continue our discussion. So far, we looked at the injection of electrons from the emitter side into the base, and we saw that due to the thermal movement primarily, and also facilitated by the electric field inside the base, these electrons will end up in the collector. So once they make it to the edge of the collector-base depletion region, they are in the collector. Now, the interesting thing is that so far, what I've assumed is that the width of this depletion region and the electric field there has no effect on the current, the total number of electrons that make it to the collector, right? Well, to the first order, they shouldn't have much of an effect because these electrons are injected from the emitter anyway, right? It sounds like it's the emitter side that controls how many electrons end up. But now, if you go and actually take a real transistor and look at its IC versus VCE, the IC, the collector current versus the collector emitter voltage, for different VBEs, right? So what this picture tells you so far is that you expect for a given VBE to see something like you expect to see something like that, right? Now, you want to see a constant current. But when you actually go and measure a transistor, this is not what you see. But you actually see something like this. And these are for different VBEs. B or C? VBE. So but this, and you know, this is very sensitive because it's an exponential. This is that exponential that we had here. So what we have is so this is, for instance, for VBE of just maybe some hypothetical number. So 0.68 millivolt, 68 volts, 0.69 volt, 0.7, 0.71, something like that. Of course, I'm just trying to emphasize how sensitive it is. This slight change in the VBE creates a major change in the current because it's an exponential dependence, right? But what I want you to pay attention to is the other aspect of this, that these are not exactly constants. This is true about any transistor, pretty much. They grow with the current, right? So if you look at it, and what you notice is that for a given change, let's say delta VCE, there is a change in the collector current, delta IC. That of course increases with the current itself. So there's a delta IC that's proportional to IC. Okay? Why is that? Let's hypothesize. Let's talk about what could be causing this. Any thoughts? What I'm telling you is that, in other words, as I increase this base emitter, as I increase this, base collector reverse bias, as I apply a larger reverse bias here, I get more current in the collector. Why is that?
Increasing the depletion region.
Yeah, as I apply a larger region, so I'm increasing the depletion region. Why is that increasing the current?
It's easier for the electrons to drop off into the E field. Or it's easier for it to travel across the base into the depletion.
Correct. Why is it easier?
Because due to the thermal motion, there's less distance for it.
Exactly. They have to travel a shorter distance. Exactly, as you pointed out. So now, more electrons are likely to make it to the other side. And of course, again, this is facilitated, also aided by the fact that the tail of this depletion region, the electric field's tail, is extended into the base, so it's extended a little bit deeper into the base. So there's a higher probability of these guys making it across because this I effectively make my base shorter. And we saw that the shorter base is better, right? So the effective base of width is shorter. Now this is called sometimes base width modulation or called early effect. It doesn't have anything to do with early or late. It's actually the name of the guy. Last name. His name is Early. His name is James Early. And so this early effect is really goes back to the modulation of the base wave. Right. Now, is it expected to see this change in the current that's proportional to the absolute current? You see that for larger DC currents, for larger ICs, my delta IC is larger too. Is that logical? Yes. Why? Because when you decrease the width of the base, you increase the chance of electrons passing, right? So the fraction of electrons that can pass is changed. But for a given current, well, for a given fractional chance increase, the larger the current, the larger net number of electrons that actually will, additional electrons that will pass, right? So if 10% more can pass, 10% of a larger number is a larger number than 10% of a small number. So what is the quantity that's kind of constant? It's the ratio, really, of the net current to the variation in the current due to the voltage, right? And therefore, we can define this quantity that the first order should be constant, IC, divided by DIC, dVCE, which we call, it has units of voltage, and we call that early voltage. Show it as early, VA, right? See, it's the ratio of the slope, the absolute current to the slope. The higher the absolute current, the smaller the slope is. Right? So it keeps the fractional change constant. Now, this voltage is really interesting. If you look at it, if you extrapolate these curves, they more or less intercept at one point, which is minus VA on this x-axis. Easily shown. Now, this is the early voltage, and we define it this way. So what does it tell me? It tells me that there is a second parameter controlling my collector current. It's not just the base emitter voltage. What else controls it? VCE, right? The collector emitter voltage. And you can capture it, you can see it's a linear thing, so you can capture it and modify your collector current expression in the following form. So this was the original expression we had, VBE over VT. Now you can add a second correction term, which is VCE over VA, to account for this. And you can see, unlike the VBE dependence, which is an exponential one, this is just a linear one. Yes?
Can you explain why the base width modulation has a linear effect? Because the reverse bias voltage actually has a square root effect on the depletion.
Okay. Yes. Yeah, well, it's a very good question, actually. It's not exactly linear. Short answer, this is an approximation. Short answer. Okay. It's more accurately a square root dependence, but you will see that the square root dependence if you extend this block long enough. But what happens is that for the range of variations that you're dealing with, it's not changing much from the linear one, so we approximate it as a linear. It's really a square root dependence, as you expect, right? Because but now also you have to remember one thing: the fact that there's the square root dependence on the depletion region also relied on another assumption, which was the abrupt junction. So if that assumption is not held, so the square root assumption is not held, it's some exponent, right? Which is not even square. It may not even be square root. In most practical cases, it's not. So it's some exponents, right? So you look at the first order Taylor term of that exponent, that's linear. So short answer, it's not. It's an approximation, but it's a reasonable approximation for the range of voltages we deal with. Otherwise, you have to have this unknown exponent. I mean, it's not unknown. It's an exponent that varies from case to case. In this case, so it's a very good question. Okay. Any more questions? All right. So, as we know, I mean, this whole thing. I mean, a lot of it's approximation, but this term is particularly important. So this is an okay approximation. This is a very good approximation. This is an okay approximation. Now, so what else? What did we learn from this? Now, first of all, do we want this effect to be large or small? Do we want this to be, in other words, do we want VA to be large or small? Or do we want these lines to be more slanted or less slanted? Less slanted, right? Because this, why is that? impact it has when we go to the circuit part of the discussion, we'll see that this appears as an output resistance and that lowers your maximum achievable gain. So this limits what is the maximum gain you can achieve out of this stage. We'll talk about that extensively later, but even without that consideration, this is the control terminal. This is the controlling parameter. I don't want the voltage on this one to be affecting what is being controlled. So ideally, I don't want to have a lot of dependence. In other words, I want VA to be as large as possible. So these lines be as flat as possible, be as close as possible to the ideal space that we want to see. Now, let's say, well, we are engineers, right? So we want VA, we say, well, that's what we want. So what do we do to the transistor? Can we do something to the transistor to improve that? Let's go back. Let's see if we can play with this transistor a little bit. Some of the parameters we can control. What is the thing that we want to do? What is causing this effect? The modulation of the base width, the effective base width, right? Because as you apply a larger voltage to the reverse bias voltage, this becomes wider, the effective base width becomes smaller. Okay? I want this effect to be minimized. I want the variation in the base width to be minimized. What is causing these variations? The depletion region, right? I want the variations of the depletion region to be minimized, at least on the base side. What do I do? What do I need? I can control, I have a knob I can turn, right, that controls which side the depletion region falls on, right? Lightly doped side, right? So we can play with the doping. Can you think of a way that I can change this so that most of the depletion region falls on the N-type, like it's shown here, on the collector side? Yeah, doped to the collector more likely compared to base. Right? If I do that, then most of my depletion falls on that side, so therefore most of the variations of the depletion region falls on that side too. Does that make sense? So that tells me that in a properly designed transistor, I have the highest doping concentration on the N side, then on the emitter side, then on the base side, and then on the collector side. And that's good. So let me ask you another question. I'm sure you've played with transistors at some point, right? Like individual transistors. Now, do you know how to tell the three terminals on the transistor? The base is relatively easy, right? If you have an ohmmeter, what do? You identify those two diodes, right? You just try different terminals, and you see that there's one terminal that has a forward current, small one, but measurable current in forward direction to the other two terminals. So by doing that, you can first determine which one is the base terminal, and also determine whether the transistor is NPN or PNP, depending on which way that current flows. Because if you reverse the polarity of your two terminals, then you will see no current flow. But then, how do you tell which one is collector and which one is the emitters? Right? So the base is easy to tell, and you can tell whether it's an NPN or PNP. Let's say it's an NPN. We've determined it's an NPN, and then we've determined that one of the terminals is the base. And we know the other two are the collector and the emitter. Do you know how to determine the other two? That's actually an interesting one. So before we answer that question, so let's hold that question there for a second. Let me ask you this question. The other question I had when I was a kid, so this is an NPN thing. So why do I care whether I connected, the collector and the emitter to the right terminals or not? Right? So sometimes it's just well, let me just do it. It's easier to connect this, and it didn't work, right? It didn't do what it was supposed to do. So what happens if I reverse this polarity? So basically, I make this the emitter and this the collector. So what will go wrong? What are the things that will be affected? I can always do that, right? I can take a 3-terminal transistor and connect it any way I want. So one of the ways I can connect it is swapping the emitter and the collector. What happens in reality to the parameters of the transistor if I do that?
It shows a harder time flying because the concentration difference.
Exactly. So first of all, my emitter injection efficiency goes down to 2. Right? Because now, instead of having more electrons than holes to inject from the emitter, I have exactly the opposite situation. Most of my emitter current will be carried by the reverse injection, by the holes back into it. Because now I have more holes than electrons in the base, that I have more holes in the base than I have electrons in the new emitter. Right? And when that goes down to 2, what happens to alpha? Alpha becomes much smaller than 1. Right? What happens to beta? It becomes some small quantity. Right? I don't have that current amplification anymore. I may even have current attenuation. Right? That's one thing. Now, let's say I can live with that for some peculiar application, right? So some pathological case. Let's say I have something that I can live with low rate. What else would be dramatically degraded? What we just talked about.
The current variation of BC.
Yeah, the early effect, right? Because now, again, I have a very bad situation because I have, instead of this, I have this side which is more highly built than the base, right? So most of my depletion region falls on the base side. So a slight change in this voltage results in a major change in the base width. So my currents, my curves for the IC versus VCE, instead of looking like this, well, they look like that, they now look like this. It's a really bad transistor. Okay? So that's why you can't reverse the polarity. So it's really, a BJT is not symmetrical in that sense. MOSFETs are. Many MOSFETs, I mean, integrated ones are. And we'll talk about that later. But now, let's go back to the question I asked you. You have already determined, so you have this 3-terminal thingy. And you know this guy is the base. And you know it's an NPN. How do you determine which one is the collector, which one is the emitter? Okay. Well, let me tell you what you do. And then you tell me if it makes sense or not. I take my ohmmeter and then take a positive to one of the terminals and negative to the other terminal, right? So this is a positive. Negative one. And I touch the base with my finger, with the tip of my finger. Okay? If I see this going to a non-zero quantity, non-infinity quantity, initially it's infinite, right? Because you are looking at 2 back-to-back diodes. Right? No current will flow. No discernible current, let's say, will flow. But now I touch the base. And if I see the current, if I see a change in it, if I see some current flowing, if I see the resistance is non-infinity, it drops to some finite value, I claim that if it's an NPN, then this is the collector, this is the emitter. If it doesn't, I reverse the polarity, and in that case it should. Tell me why that's the case.
Can you say the case one more time?
Okay, so I'm connecting the positive terminal to this guy. So think about it as a battery. Right? I'm applying a small battery between the collector and emitter. Positive terminal to the collector, negative to the emitter. If that were the emitter. If I touch this and if I see it changing the resistance, if I drop in the resistance, then this is the collector, this is the emitter. If I don't see it change, it's the other way around. This is the emitter, that's the collector. And you can verify that by swapping and then try it again. But why? What's happening?
Are you warming the...
No, it has nothing to do with that. Just touch the tip of the terminal. Just touch it. You will see.
We have some potential.
Well, I have a lot of it. But, so do you guys. But, no, I have charge in addition to it. Well, so my body has some electric charge. And when I touch this, I'm not necessarily at the same potential of this. So there will be some injection of charge into this thing. A little bit of charge, basically there's a little bit of base current. As soon as I put a little bit of base current in there, basically it means that I build up a VBE. As soon as I build a VBE, there will be current flowing in this direction because basically that charge gets amplified by beta, right? Because that current is amplified by beta. IB is amplified by beta. So I put a little bit of IB in there, it gets amplified, so there will be large enough current so you can see something. But now, if it's the transistor is reversed, beta is really small. That charge is not enough. In case of some transistors, you may see change in resistance in both directions, but the change would be substantially greater when it's connected this way than the other way around. Does that make sense? Okay. All right, so that's just a little piece of trivia, but it's based on what we learned about transistor. All right, any questions?
Yeah, that's a quick one.
Yeah.
All the graphs for the early effect, you have VCE. Wouldn't it make more sense just to do VCB?
It does. It does make more sense to do VCB. But the thing, that's right. But it's a very good question. The way, it really goes back to the way we use the transistor. Right? It's more convenient, and in fact, in most practical cases, more useful. Plotting versus VCB, not VCB. The reason is that in forward active region, which is the region I've shown that this junction is forward bias and the other one is reverse bias, this voltage is almost constant. Doesn't change a whole lot, right? Because the current is so strongly dependent on that it's around 0.7, 0.6, 0.8, right? But most of the variations happen, this VBE is here, most of the variations happen here, across the base collector junction, right? So if I plot it versus VCE, I'm not losing anything in terms of variation. I'm just adding the 0.7 to everything, or 0.7 to everything, or subtracting against 0.7. But then, the point is that this is more conducive to the way we use the transistor often, which is the common emitter configuration. But in terms of what you said, in terms of independent variables, it makes perfect sense. What you said makes perfect sense. You have to actually show, it's better to show it versus VCB. But for convenience and what it applies to, it's better to show it in terms of VCB. Very good question. Any other questions? Alright. So now let's go back to our discussion about the head-to junction. We said that HBTs help with emitter injection efficiency, right? But let's go back and, I'm sorry, before I talk about that, I have to say something. So let's talk about something else for a second. Now, we said that the doping concentration here is higher than there, and the emitter is the highest, and then you have to go to the base, which is lower, and then you go to the collector, which is even lower. But what does that mean in terms of the resistance of the collector? If the doping level is low, it means that the resistivity is high. Yeah, it's not as thin as the base, but if I go, let's say 2 orders, so let's say from 10 to 19, 10 to the 17, and then 10 to 15. That's reasonably low, so resistivity is high. So I have a reasonably large series resistance, RC, here, in the collector. Which is not a good thing, because that's where most of my current goes. So if I have a large RC, then I'll have a reasonably large voltage drop across here. So, but this is intrinsic, this is internal to the device. So the voltage I can actually see and use is here. So I don't want to lose a lot of my voltage swing inside the transistor. In addition, it generates heat and all that sorts of things, right? So I want to minimize its resistance. How do I do that? In this picture, just in the picture I've shown. Is there something simple I can do in this picture?
Change the dimensions of that.
That's one way. So for instance, what you're suggesting actually is to make the collector extend beyond here, so maybe extend it, something like that, right? And that's in practice done the way the transistor is. That helps to some extent. Can I do something else? Let's say, in addition to that, or let's say I can't do that for some reason, I have to keep the rectangular design. Anything else?
Use a non-uniform doping profile.
Say again?
Non-uniform doping.
Non-uniform doping profile in the emitter, in the collector. How? Correct. So that's what.
Keep it lightly doped towards the junction.
Exactly. Right? I need the light doped N-type only close to the junction. So if I know my depletion region is not going to extend beyond here, I don't need to make this light doped all the way down, right? So I can make it, this region is N, or let's even call it N minus, and then I can make this N plus. I can make it very highly doped. Because as long as the depletion region doesn't go in there, it doesn't affect anything. But when I do that, I reduce my resistivity substantially, and therefore I reduce the total series resistance. So almost all bipolar transistors today have this built one way or another. I mean, in integrated minus or low doping profile all the way. It's needed here. Also has another benefit, which is basically making this junction more of an ohmic contact as opposed to a, it can result in a non-ohmic shock if you're not careful. You can make a diode that should be connecting with the metal, but that's the second thing. So that's one way to improve things. But still, I mean, I have finite resistance here. I lowered it somehow, but I still have RC that I want to lower. Is there something else I can do to help and improve this?
Increase voltage, have more volts.
But the voltage, if I, well, how would it increase the voltage? It would increase the number of volts, right? The voltage would increase the number of volts. So what do I need to do? Well, really, it boils down to being able to have a larger N, right? Well, more accurately, ND. Right? The doping level. I want to be able to use a higher doping level. But we just saw that that's conflicting with what? With the reduction in the early effect. Because we wanted this to be low, so the early effect is low. But what do I need is this for ND to be lower than NA, right? Right? What if I could somehow increase my NA? I could increase my ND too, right? And keep the ratio constant. Because I want the ratio to be large. But what does that conflict with? It is in conflict with. If I increase my NA.
Recombination with.
Yeah, so it will lower my emitter injection efficiency. Right? And the recombination, but it's primarily injection efficiency. So I have to increase this guy too, if I have. But there's a limit to how much I can increase this. I mean, beyond a certain point, it just becomes, there's a limit to how many dopants I can introduce. They call it a degenerate case. But beyond that, it doesn't introduce additional holes or electrons. So there's a limit to this. So if I'm at the limit already, I can't go higher. But there was something else that we talked about that comes to help me here too.
Like the collector there.
Well, but still, I mean, there's a limit. I mean, I do all of that stuff, but still, I'm at some level, right? True, I can do that too. In this direction, right? But again, that's limited by the depletion region. So if I'm already at a point where I can only maintain my depletion region inside, contain it, then that's all. Remember the band gap engineering stuff we talked about? Do you think it can help or hurt us? Just the way you've done it. What did it allow you to do? What we did is to reduce the, increase the potential barrier height for the holes only, right? So for a given doping level, it gave me a higher emitter injection efficiency, correct? Higher gamma. But now, if I have basically, so that means that for a given gamma, I can relax the ratio of the doping concentration on the emitter and the base side. So it means that for a given gamma, I can actually now, if I have on that band gap engineering, I can increase the doping level on the base side, right? Maintaining the same gamma. So I can make up for it, right? So it allows me to increase NA because I have gained through the band gap engineering and hence increase ND and therefore reduce the resistance of the collector and the resistance of the base. And that's why HBTs are generally kind of faster devices than standard homological structures. Does that make sense? So it's an indirect effect. The fact that I don't need such a large difference because I have a lower band gap here and there allows me to increase this level and hence increase this level while maintaining this ratio constant. So without degrading my area effect, I can maintain the same gamma with the aid of the difference in the band gap and hence improve the situation. Okay? Does it make sense? Alright. Now, having said all of this stuff, right? So let's go back to our transistor model and see if we can make the complete model for it. So what we have so far is this model, this picture. But now, this doesn't really capture if I use the transistor in any way other than forward biasing the base emitter junction and reverse biasing the collector. base junction, right? I want to have a model that captures all of these effects at the same time. If I reverse bias both of them, if I forward bias both of them, something like that. Now, how do I do that? Well, I noticed that I really have a second transistor, if you want to think about it. If I use the transistor in reverse mode, I have another model, just like that. So, this is my original transistor model. So, this is the emitter base, and this one, so this is, let's say, let's call this IF for the forward transistor, IES, E2 VBE over VT. And this is alpha IF, alpha F, the forward output. This is the collector. Now I have another transistor, but if I use my transistor in the reverse mode, as we discussed, right? It's a really crummy transistor, but nonetheless, it's a transistor. It's like this. And then let's call this I reverse, IR, which is ICS E2 VBC over VT. And then this is alpha R, IR. These are connected. This is the base. So this is the complete model for the transistor, the two of them in parallel, right? The forward transistor and the reverse transistor. And this kind of subsumes that, right? Because think about it, if this is reverse biased, this current is 0, right? This diode is off, therefore this current is 0, so these two disappear, so this is what you're left with. In fact, you often redraw it slightly differently, so you put the two diodes in one place, and the two dependent current sources. Alpha F, sorry, by F, and this is going to be IR, which is ICS E2 VBC. Okay? This is called Ebers-Moll model after the two guys who came with it. And this is valid in all combinations of forward bias and reverse bias for the transistor. So there are 4 combinations, right? You can think about it. So we have 2 junctions. So we have the base emitter junction and the base collector junction. This can be off or forward, let's say reverse or forward. And this guy's going to be reverse and forward. So when the mode that we talked about the most, it's called the forward active region, which is when the VBE, base emitter junction is forward biased and the base collector is reverse biased. So it's called forward active region, or FAR for short. This is the mode where we have a large beta and all the good gain qualities. Fine. Now, what can you say about the transistor when both junctions are reverse biased? It's pretty much off, right? I mean, what you have is some parasitic capacitance to the junctions, and then there may be some leakage current, but pretty much it's off. So we call it off. And what about the case where VBE is reversed and VC is forward? That's called the reverse active region, or RAR. Okay? And we saw it's a crummy transistor, right? It has all bad properties, but it's a flex transistor. Now, what if both junctions are forward biased? Both of these diodes are forward biased. What happens in that case? Both of them inject a whole lot of electrons into the base. It doesn't blow up really. I mean, the base is filled with a lot of excess electrons. So you have a lot of minority carriers being injected into the base, so you have to provide a whole lot of holes to recombine, because they're not going anywhere else now. They're all being dumped into the base. So your base current, that green stuff, becomes very large. So you carry a large current, goes into the base, and then it has comes in. Pretty much it becomes like 2 diodes. Forget about these guys, it just becomes 2 diodes, forward biased. At the same time. And that's called saturation. Transistor saturated. We'll talk about it in a second. Okay, so how do we modulate the saturation? Well, think about it. At the edge of saturation, right, when the saturation is about to start, your VBE, your base emitter junction is on, right? So for typical levels of current, that's about 0.7 volts drop. So this is the base, this is the emitter. Now, the other thing you have to keep in mind is that, let's say we start from forward active region and keep lowering the collector voltage till this one starts going into it starts turning off this diode. When does that happen? Well, you need at least about 0.5, 0.6 to get to any reasonable level of current, right? So at that level, what you really have is something like this. So this is something like 0.5 volts drop to the emitter. I'm sorry, to the collector. So when it gets about 0.5 of this, so this junction is forward biased by about 0.5 volts. This is about to start turning off, 0.5, 0.6. Right? That's the edge of just starting carrying some substantial current. Now, you can think about this, well, it's 0.7 up and 0.5 down, so I can redraw it exactly, equivalently, as a 0.1 to 0.2, or in this case it would be 0.2, let's say 0.2 volts here. If I have a battery like 0.2 volts here, that would be about it. So 0.1 to 0.2 volts. That's the way we approximate the transistor in many cases in the saturation region. In fact, you can actually use the Ebers-Moll model and calculate what happens in the transistor, exactly what the voltages are in any mode of operation. So if you want to know exactly what the voltage is, you can just plug in, if you calculate ICS and IES, you can plug in, you know alpha R and alpha F, just plug it in and you can calculate exactly what this voltage is. But the point to take away from that is that when you get to saturation, the voltage between the base, between the collector and emitter is quite small. And that's in those curves, this part of the curve. So it's this part we're talking about. When you have a very small VCE. And once you get out of that, you're in the forward active region, which is this region. For analog design, almost always we are operating in this region. But it's important to understand what this region is because you don't want to enter it, or when you enter it, it's important. Now, from dynamics perspective, it's also interesting because once the transistor, and we'll talk about it a little bit later, but once the transistor enters this mode, what you have a huge buildup of minority carrier charge in the base, right? Because both junctions, both the collector and the emitter, are dumping electrons into the base, in the case of an NPN, or holes in the case of a PNP. Minority carrier charge. Now, this has to go away through recombination. So if you want to turn the transistor off at that point, even if you cut so let's say for the sake of argument, the transistor is in saturation, and there's a lot of base current, and all of a sudden I want to turn it off. Let's say I want to say, well, I disconnect my base, it should turn off, right? Not quite, because when I disconnect this current, there's this huge amount of charge left, still in the base. Huge number of electrons that have to go away. Where do they go? How do they disappear? They have to recombine. So it will take time for it to recombine, and during that time, there will be net current flowing through here. So the transistor doesn't turn off that easily because of this charge storage. And we'll talk about that in a second, the dynamics. We'll talk about the dynamics. But that's the essence, that's the physics behind it. Okay, now, so far, everything we've been talking about has been kind of static, low frequency, DC kind of thing. But now let's see what happens in the transistor when you start moving things, start moving things a little bit faster. Now, one of the things to keep in mind is that what is the parameter that really controls the collector current in this picture? Well, it is really this voltage, but what is the thing that really controls how much collector current at any instant in time you have? It's this charge in the base, right, that had this kind of funny distribution, right? So let's call it QF or forward. So this is the minority carrier charge in the base. Think about it. If on the average, my electronic charge in the base is QF, coulombs, okay? And let's say on the average, it takes an electron tau F to get from this point to that point on the average, for an average electron, right? What can I say about my collector current in terms of these two parameters? I can see that my average electron collector current is going to be QF over tau F, right? The total charge divided by the time it takes this charge on average to get from one edge to the other edge. Does that make sense? So that's one thing, I know. But now, what I'm interested in is really the variations in this charge. So I'm interested in dQF dt, the temporal variations of this charge. So let's look at the various sources and sinks for this charge. Where does it go? What affects it? So where does this charge, what builds up this charge? What helps you build up this charge in forward active region? IE, the emitter current, right? I'm assuming that alpha is close to 1, okay? So most of the current is carried by that. So IE is what acts to this. But most of the IE doesn't end up in the base, right? On the average. Where does it go? What takes charge out of the base? The collector injection, right? Minus IC. So IE is the amount of electrons I'm injecting into this. IC is the amount, a good fraction of them that I'm taking out. So the difference is remaining here, right? Now, what else happens? I'm also losing them to recombination, right? This process. So how do I account for that? Well, how much recombination I have if I have 0 electrons in the base? 0, right? If I have 100 electrons in the base, I have a certain amount of recombination. But if I have 1,000, now how much more do I have? About 10 times more. So the probability of recombination is proportional. It's fixed for electron. So the total number of recombination electrons lost to recombination, or total amount of charge lost to recombination, is proportional to the amount of charge I have. The more charge I have, the more of them can combine, because a fixed fraction of them will combine. So it has to be, I'm losing them, it has to be proportional to QF, and the proportionality constant is called 1 over tau b, which is the time constant associated with the recombination. It's a relaxation first order process. The base time, or you can think of it as a proportionality factor. Okay, so this is the basic equation governing the transistor. And in fact, but I know one more thing. Due to KCL, what can I say about this? As long as the transistor's dimensions are much smaller than the wavelength I'm dealing with, which in practically all the cases I've dealt with in my life, it has been the case. This is what? KCL holds, and this is, what is this quantity? IC minus IC. It's IB, exactly, basically. So I can rewrite that QF over tau B dQF dt. So you can see that the dynamics is governed by this first order equation, the forward active region. Okay. What does it tell you? Well, it tells you some interesting things. For instance, one thing it tells you is that in steady state, what does it tell me? It tells me that, well, this is 0 in steady state. Right? So IB is QF over tau B, which I know is, by the way, IB is IC over beta. And IC is QF over beta tau. So tau F, so this becomes QF over beta tau F. So between these two guys, one thing I notice is that beta is tau B over tau F. Or in other words, tau B is beta tau F. So I don't even need to count. I don't even need to give you tau B. If I give you beta and tau F, the forward transit time, the average time it takes an electron to get from here to there. That's an important parameter in the transistor, by the way, which determines its speed. You want tau F to be as small as possible. But if you know tau F and you know beta, you can calculate tau B. Okay? So that's one thing. And of course, it tells you that you can use this first order equation to calculate the response of the transistor. So you can, for instance, you want your homework, I think in the next homework problem set, what you will do is very simple. You have a transistor that's on, and then you turn it off. And then you determine what happens to the collector current. And you will see it doesn't turn off immediately because there's base charge. So that base charge carries some additional current. So you turn off the base. So the base voltage goes like that. Let's say turn it off, right? But the collector current does not die off immediately. It dies off exponentially, as you can see from the first order equation. And you will do it yourself. It's very straightforward. So it takes time for the transistor to turn on too. Why? Because you have to build up that base charge. In the beginning, when you turn it on, when you apply voltage, it doesn't immediately turn on. Right? It takes a little bit of time for this IB to replenish, for this difference to make the base charge. And therefore, what it means is that IE has to be greater than the steady state ice, what would have been in steady state. So you have to basically have a larger current initially, or IC is smaller, in other words. So your collector current does not established immediately. Okay? And that determines how fast the transistor can operate. And we'll see that actually when you calculate the FD of the transistor, which we'll do probably next time, that's determined by what? By tau f. That's one of the parameters. Now, that's one of the things that affect the dynamics of the transistor. What else affects the dynamics of the transistor? Right, we got two junctions there, right? There's a base emitter and the base collector junctions. There are these two junctions. And each one of them has a capacitance. We saw that, right? We calculated the junction capacitance. So these capacitors need to be charged and discharged. When you change the voltages, you need to charge and discharge them. So you need to provide some additional charge, so you have some time constants associated with that. As we'll slow you down. And one of the things we'll do later on when we do the dynamics of the transistor, actually we'll do the E114B, the next part of the course. What we'll do is, later on, is to look at this and calculate the response of the system and the circuit based on these individual time constants, and for that we need to calculate these individual capacitors. Okay, now what we'll do next time, we'll quickly use this knowledge that we have developed and go and derive the complete small signal model for the transistor. So far what we have is large signal. Everything is it's a nonlinear model, the way we have it. What we'll do next time, we linearize this model around an operation point. So we say, well, if we establish a certain bias, quiescent point, we say, well, okay, we are around this point, and then we can linearize this nonlinear model. And we come up with a linearized model, which is the so-called small signal model, which is valid for small perturbations. Perturbations on this operation point, and we'll derive that, and we'll see how those parameters of the small signal model are related to these large signal parameters that we derive. Use that to calculate the cutoff frequency of the transistor. We'll see what is the maximum frequency the transistor can operate at, kind of. And then we'll take it from there, and then I think we'll continue our discussion. We'll start our discussion on the MOSFET. So next time I'll give you a handout on the MOSFET. So we'll talk about the MOSFET. Now, before we go, let me talk about something quickly for a minute. You know, the first transistors, I don't know if you've seen it or not. Well, I'm sure you've seen pictures of it. Actually, I have a picture. I probably should bring it in next time of the actual first transistor we made. It was a Bell Labs. I don't know where it is now. But have you seen that picture? It looks like this. Kind of. I'll bring the picture next time. Like a thingy up there. And there. Looks like that. I mean, of course, this is the tiny part. Right? The first transistor they built. Right? It looks like that. Do you know what that is? What it is? Okay, so this is what it is. This is the base. Okay. This is a piece of semiconductor, right? There's a certain level of doping. And that's why they call it a base. You see, this is kind of the base now. But now, this thing, if you look at it, it was a wedge, so it's a wedge. They took a very tiny one, and then they put a layer of copper on this, kind of like a very thin copper foil. Started from the side, and they had it on the other side. Okay? And then, under the microscope, they cut the tip off. So now, if you look at the cross-section of this thing, it looks like that, magnifies quite a lot. It's copper here, it's copper. And then made contacts here with some wires that are these kind of springy-looking things. Now, and they put it on top of the semiconductor. Now, what this does, it creates two junctions because the copper starts making something similar to a shock contact with the semiconductor. So you can think about this as forming a little hole here, a little hole here. So this is kind of N plus N, and this could be a P, the base. And then they made the third connection here, the base. So you can see they created this NPN structure, right? And that's why they call it a transistor. It's a trans resistor. They control the resistance between these two through this voltage. The third terminal. And that's the base, collector and emitter. This is actually not a BJT lead. This is called a point contact transistor. We don't make them like that anymore because they're not very good. You can tell me why it's not a very good transistor, right? There are many reasons for that, of course. It almost defies everything that you said we should do to make a good transistor, but it's the first one. You win a Nobel Prize for this one. If you're the first one to make it. So it doesn't have to be perfect, but the first to make it. That's quite new and novel. So, what's bad about this? Let's talk about that at all. What are the bad things about this transistor? I mean, compared to what we made before. Well, the base is huge. Right? The size, yeah. And then, but emitter injection efficiency can be lousy, and your early effect is going to be huge. Doesn't matter. You make something that affects everything else that follows. And a lot of people will come later and analyze the heck out of it, and a lot of people will come and improve it substantially. But still, it's actually ask someone who invented the first transistor, or what was it like? It's like this. So the lesson takeaway, your research field. You don't have, if you want to do something really revolutionary, it doesn't have to be perfect. It has to be good. It doesn't have to be perfect. All right. Well, have a good rest of the day, and I guess I see you on Friday. There are no more questions.